Sorry to be late, everyone. I think I'm muted.
Yeah, now I think now it's.
Okay. Sorry to be late. I had a little bit of subway problems, but today's lecture is a little short anyway, and we can't run over because I have an emergency dental appointment.
Emergency.
So long lecture. Okay, so where we left off is we have the BWR equations, and then our focus, since the double commutators have all been done by graduate students of the past, the focus then is the spectral density function. And that's what we want to talk about today. So again, the power spectral density function is the real part of the Fourier transform of the autocorrelation function for the spatial functions, rotational, tumbling, etc. And the autocorrelation function is even function of tau. So you'll see it variously written as t minus tau or t plus tau. They're equivalent because the function's even. And then there's this factor of 2 depending on whether you extend the interval to minus infinity or not. The spatial functions then are all products of various parameters of the Hamiltonian, delta sigma, B naught, the distance between pairs of spins, etc. And then the orientational dependence, which is captured by the spherical harmonic. So the C's contain everything that's not orientation dependent, and everything that's orientation dependent goes into the spherical harmonics. Now, why the spherical harmonics? We've talked about that some already, that if you have a spherical harmonic that corresponds, for example, to a p orbital, when you rotate, you still have a p orbital. You don't turn into a d orbital. And that's reflected in the fact that the rotations of the spherical harmonics are performed by these Wigner D matrices, but the rank K remains constant. So we start with the second order spherical harmonics, we end up with the second order spherical harmonic. So d or p orbitals stay p orbitals. These Wigner D matrices are functions of the Euler angles, and you saw this, of course, in Ann's lectures about how the tensors get transformed by rotation. That also depends on the Euler angles. The D matrices, of course, have definitions. They have orthogonality conditions. This one here they are for rank 2. We won't be using them so explicitly in this part of the course, but of course they come up again in solid state NMR. So here's what we have. If we make the substitution for the spatial functions, we have the joint autocorrelation function for the C's and the spherical harmonics. And that's pretty difficult to deal with analytically. So if you have to deal with such a coupled problem, it's almost always a computer calculation rather than an analytical calculation. But if we want to, and it's easy to imagine conditions where this would be true. So if you have a protein that's a clamshell and it has a compact form and a more extended form, when the clamshell opens, distances between spins are going to change, and you might expect the tumbling to change in those conformations. So there, distances and orientation may be correlated with each other. So if we're going to make any analytical progress, the first step is to pretend that we have independence of the variables contained in the C's and the orientations, so that the joint correlation function can be factored into the product of an autocorrelation function for the C's and an autocorrelation function for orientation. Yep.
My tensor of interest is CSA.
Pardon?
If I'm looking at the CSA tensor,
Mm-hmm.
then do these coefficients C not become time independent?
So if you regard then the CSA as being a constant, right, then these C's become constants.
Right.
Mm-hmm.
But they may not be constant.
Well, the chemical shift anisotropy, I think, to a very good approximation is, you know, in the absence of chemical changes.
Right.
So then, if it's a constant, as just said, then we just have those constants squared times the orientational spectral density function. And the tables I showed you yesterday at the end of the lecture all made that assumption that the physical parameters are fixed, the bond distances or the distances between spins were fixed. Now, there's two other limits that are easy to talk about. If whatever parameters are in the C vary slowly compared to the reorientation, then the autocorrelation function for the C's won't have decayed very far before the orientation function or orientation has decayed to zero. So if we have some slow motion changing the distance, but tumbling is fast, the autocorrelation function for tumbling will go to zero before the autocorrelation function for the distance has really decayed. So under that kind of timescale separation, we can replace the autocorrelation function for the physical parameters by its value at time zero, and that's just the variance of those. So if you think about protein noses, where the distances might vary, what might be a case where you would expect slow motion internal to the protein that would change the distances to some spin? This is actually
global composition is changed.
right, but I'm thinking about some specific thing. This actually is problem 14.
Yeah.
Ring flips. So aromatic ring flips can be quite slow and relatively slow in a protein, but they're fast enough that you usually only see one resonance. Say for the delta, you have two delta hydrogens, but you only see one resonance. because the flipping is fast enough on the chemical shift scale to average them, but that's slow on the tumbling scale. So if you have an NOE to some other proton, it might be closer to one of the delta hydrogens than the other. And then the ring flipping is averaging those distances. And if the ring flipping is slow, this says we should average the square of the C's. C depends on 1 over R cubed. So this says we should average 1 over R to the 6th. So we take the two distances to the two paras and then average those two distances as 1 over R to the 6th for the one plus 1 over R to the 6th for the other. And inside of various structure calculation programs, this is an option that you could turn on, is to do 1 over R to the 6th averaging for ortho and parasites and phenylalanines and tyrosines, for example. The other limit would be the internal motion is fast compared to the reorientation. And then the autocorrelation function for the C's will have decayed to its final plateau before anything has happened from overall tumbling. And the plateau is just the square of the mean. And in that limit, we would calculate the average of 1 over R cubed and then square that. So what's an example in a protein where the internal motion averaging the distance might be very fast?
Let's see here.
A methyl group, right? Methyl group, you have 3 hydrogens. Here's a 4th hydrogen over here. As the methyl group rotates, the distance from any one hydrogen to the remote group changes. And this says we should average that distance as 1 over R cubed and then square. And again, in some structure calculations, one can turn that on as an option. But those are basically the 3 kind of analytical limits. The physical parameters are constant, they vary slowly or they vary quickly. And in between, right, it's all a job for computer calculation. And that leaves us then the orientational autocorrelation function, which is just the autocorrelation function of the spherical harmonics. And again, we said in isotropic space, the spherical harmonics for the autocorrelation functions or spectral density functions for the different spherical harmonics are all just related to each other by factors of -1. So that we just have to calculate one autocorrelation function, and we might as well do it for the 0th order autocorrelate spherical harmonic, because that's the easiest. Here, for example, would be our 2-site jump model. We decided at the end of class that this could be represented by a rank 0 spherical harmonic. And if we just plug in, we get this result for the autocorrelation function for the 2-site jump model. I'm just asking Mathematica to do the arithmetic. For the rigid sphere, the autocorrelation function decays as a single exponential. Then we can plug this in. We have to then do the integral over this autocorrelation function. And here then, capital J of omega for an isotropic sphere is 2/5 tau c over 1 plus omega squared tau c squared. And that's kind of the equation you see most often in solution as just an example autocorrelation function. Now the factor of 2/5 could have been lumped somewhere else. So depending on what paper you're reading, you might see a factor of 1/5, or you might not see any numerical factor at all, in which case the 2/5 got put in with the C's. Again, if you're trying to do quantitative calculations, you have to pay attention to where all the numerical factors go. This function, by the way, and I'll add a graph. If omega goes to 0, we just have tau c, 2/5 of tau c, and that's just our adiabatic limit again. J0 is just tau c, and we just have variance times tau c again. As omega increases, this function decays rather slowly until omega is equal to tau c. And at that point, the function will have decayed by a factor of 2. And then you get a rollover, because as omega gets to be much bigger than tau c, the numerator, this omega times tau c squared, becomes much larger than 1. So we can ignore the 1, and then you see we just have a decay by 1 over omega squared. So we go from this rather slow decay, and then there's a rollover where the decay is very rapid as 1 over omega squared. And that's a property of basically all the spectral density functions we'll care about, because if all motions are on the time scale we're interested in, if all motions are overdamped, then the autocorrelation functions are just going to be sums of exponentials. And the Fourier transform of the sum of exponentials is just going to be a series of a sum of terms that look like this term with different time constants. That reminds me to say something else about this. If you have analyzed nitrogen 15 relaxation in solution in proteins, measuring R1, R2 NOE, which is a very common thing to do these days, you would see that the bond length that's used, the NH bond length that's used, is either 1.02 angstrom or 1.04 angstrom. But if you go and look in, say, a molecular dynamics force field, you're more likely to see a bond length of 1.01 angstrom. And the difference has to do with the averaging. The bond is always vibrating, right, on a femtosecond time scale, and that's changing the dipole interaction between the hydrogen and the nitrogen, and there's 0 point motion of the hydrogen that's moving it out of plane, etc. So when we use a bond length for these calculations in NMR, that variation is very rapid. So we actually need to take the square of the 1 over r cubed distance. And that turns out to be a little longer than what you would find in a quantum mechanical force field. And it's a different kind of averaging from, say, neutron scattering, where you could also see the hydrogen. So the reason there's both 1.02 and 1.04 in the literature has to do with how much of this off-axis motion of the hydrogen bond, or the height of the hydrogen, is taken into account. Anyhow, that's another case where this fast averaging is important in deciding how you handle the dipole interaction between the nitrogen 15 and the hydrogen. Of course, the protein might not be a sphere, or RNA molecule might not be a sphere. And the next step up in complexity is an ellipsoid. So either an American football or a flying saucer, where you have one unique axis and then two rotationally identical axes. There's a diffusion equation for that we can then solve for the probability distribution for orientation of the ellipsoid in space. There's a standard way of doing this that I don't really want to spend time going through. You can go through it if you want. And at the end, we have an expression for the autocorrelation function for the principal axis system of the Hamiltonian. And again, this probably looks like expressions you saw from Anne. The end result is that each of these autocorrelation functions of the D matrices looks like a single exponential decay. And you can see we have to sum over an index on the D matrices. The end result of all of this is we end up with a sum that turns out to be 3 terms in it, because there's some degeneracy from the symmetry of the ellipsoid. You might have expected 5 terms, since we have a rank 2 spherical harmonic has 5 elements, but there's some symmetry because of the ellipsoid. So we have 3 time constants, 3 amplitude factors. So the overall autocorrelation function is a linear combination then of 3 exponential terms. And these factors here, the A's, then depend on the orientation of the Hamiltonian. So this also is assuming a uniaxial Hamiltonian. Orientation of the Hamiltonian in the principal axis frame for diffusion. So what it means is it will have different relaxation rates for, say, dipole vectors, say NH vectors, that point in different directions in the ellipsoid. So an NH vector, if we imagine the ellipsoid as an American football, an NH vector that points along the axis, the long axis of the football, is not affected by reorientation around that axis. Whereas, and is only sensitive to reorientation along the 2 short axes. Whereas a vector, say, that's along the equator of the football sees the effect of rotation around the long axis and the short axis. So if we collect relaxation rates for many spins, many NHs in a protein, there's going to be variation that comes from the different orientations in the molecular frame, which means we can try to extract information on the diffusion tensor from the relaxation rate constants. So it turns out that that is a very precise way of obtaining, measuring diffusion anisotropy of molecules, assuming that you have reasonably good coverage of space by the orientations of the NHs. So it stops working very well, for example, in a 4-helix bundle. In a 4-helix bundle where you have 4 helices pointing in the same direction, the NHs all point more or less in the same direction along the helix axis. So you don't have good coverage of the sphere in orientations. In that case, you might imagine adding in another spin pair, for example, C alpha H alpha. The relaxation is rather harder to measure, but the C alpha H alpha vectors are more or less orthogonal to the axis of the helix. So they give you access to the other orientations that you need. This leads to another complication you might imagine, which is that if we're measuring NH relaxation, we also have CH. I mean, we also have CSA of the nitrogen. And the tensor, the CSA tensor, even if we imagine it as being axial, it's not completely axial, but if we imagine it as being approximately axial, it doesn't point quite along the NH bond vector. It's tilted by probably 16 or 18 degrees. So now you can see there's a problem. If we have an American football and the NH vector points along the long axis and doesn't see rotation around that long axis, the CSA tensor is going to be pointing away from that axis. So it is somewhat sensitive to that rotation. So analyzing the internal dynamics then becomes much more complicated. It's mostly ignored when we do when we're analyzing N15 relaxation. But as the measurements become more and more precise, then this becomes an issue. And Christina Redfield has a paper now many years ago showing that the data is good enough to see this effect. But most of the programs for analyzing N15 relaxation don't really take this into account. So there's room for improvement on the software side. And if you go to other spins, the situation can get even worse. You saw from Anne that the CSA for a carbon in an aromatic ring, unique axis is orthogonal to the ring, but and perpendicular then to the dipole interactions. So there the problem gets to be even worse and not even approximately in the same direction. Yep. And I should just say if we Fourier transform this, then we just get a linear combination of these terms that always look the same. Time over 1 plus omega squared time squared. Yep.
Is it possible to sort of say that the amide CSA is, I mean, I don't know what's the magnitude of the amide CSA compared to the dipole. The dipole is like 10, 11 kilohertz.
Mm-hmm.
How much is there like a magnetic field at which I can keep the amide CSA small but have enough resolution to view?
Yeah, unfortunately, no. So at around 900, they're roughly equal to each other, which is why the Troisi effect is effective at 900. And you scale quadratically with the field, right? So if you cut the field in half and say you go to 400 megahertz, you'll still be 25%. The CSA is still 25% of the dipole interaction. So, and for a large protein, 500 is always already getting difficult from sensitivity and resolution. So, yeah, no. In fact, it's better for us that it's larger because the Troisi effect is so important. Mm-hmm.
One out of the, is this why zero field NMR is they get the CSA?
Well, the CSA effects are gone. But then all of the J couplings are now strongly coupled. So weak coupling, remember, requires that the difference in chemical shifts be large compared to the J couplings. And then you truncate the IX, SX, IY, SY, and just keep the IZ, SZ part of the Hamiltonian. So if you go to zero field, then you have the full coupling tensor. And you have to take that into account. So even before you get to, zero field, at very low field, this becomes an important effect. And one of the things you can do at low field is do a Toxie experiment that works spectacularly well, because now the J couplings really are strong coupling. So Fabien Farage in Paris has a machine where he can shuttle a low frequency, do a Toxie, and then come back to high frequency for measuring the spectrum. I think anything else that could be said intelligently about zero field NMR would require that we have Ann with us today. Ann, you want to say anything about zero field NMR? That's maybe a no. Now there's a really elegant approach from Raphael Bruchweiler. Well, what would happen if we didn't have an ellipsoid? So if all three diffusion tensor axes were different from each other, and our molecule looked like a potato, for example, which it probably does in reality, then we'll have 5 exponentials rather than 3. We won't have this collapse by symmetry. So the equations, again, are just going to be a linear combination of exponentials. The prefactors become much more complicated, and you have 5 exponentials. Raphael worked out a very elegant approximation that if the molecule isn't too far from being spherical, one can analytically determine the fully anisotropic diffusion tensor from the relaxation rate constants. And the key idea is that if asymmetry isn't too large, then each NH group that can be represented as if it's tumbling isotropically with a single exponential decay, but that the time constant varies depending on where you are in the molecule. Because depending on where you are in the molecule, the mixing from rotation around the different axes will be different because your orientation is different. But essentially, if we have these 5 exponentials, but they don't deviate so much from each other, then there might be an approximate single exponential decay. And he worked out a very elegant way of doing this. And you can look up this paper. What I've done here is something much more simple, which is to say that suppose we have our 3 exponentials for the axially symmetric molecule. It would work the same for an anisotropic molecule. And then I expand to first order in Taylor series. Then I can do the sum, obviously. And then if I plug everything in, well, first of all, after I do the summation, because the A's add up to unity, this looks like the first order exponential of an average average decay. A tau got lost somewhere. There should be a tau here. So I plug in for the A's, do a bunch of summations and say that looks then like a isotropic decay, single exponential, with a diffusion rate that depends on orientation, and this diffusion rate is shown here. It depends on the spherical harmonic, as you might expect, and on the difference between the two axes of the ellipsoid. In this, 6D is 1 over tau c. I could have written it as tau over tau c. It's just a little more convenient in this case to use D, a diffusion constant, rather than a diffusion time. And the 6 comes because we have a second order spherical harmonic. So that turns out to be a factor of L times L plus 1 shows up. And because we have L equals 2, we have 2 times 3 equals 6. This actually confuses people sometimes, because if you have a measurement like a linear and an optical linear anisotropy measurement for diffusion, that depends on the first order spherical harmonics, and then L times L plus 1 is 2. So there's a factor of 3 difference between the time constants you measure using a linear anisotropy measure and versus one that depends on second order, like either NMR or fluorescence. Occasionally people get confused. A linear measurement might be you oh, that's enough about that.
Okay.
Anyhow, this gives the same result for a ellipsoid as Raphael's more elegant approach, but perhaps is a little simpler. It all fits on one page. And then you can see, if we know the orientations, we can again extract an estimate of the difference between the two orientations, and then D iso is just the average. So then we can figure out both D parallel and D perpendicular.
That's been used to get constraints to structure determination, getting orientation.
So Nico Chandra has done some of that. As it turns out, if you can align your protein and measure residual dipole couplings, those turn out to be easier. So cases where you can get alignment, people would prefer to do residual dipole couplings. The math, as you can see, is going to be almost identical.
Yeah.
The only real difference in the math is for the residual dipole coupling, you have a traceless tensor, which is a bit of a help. But if you can't align the molecule, then the relaxation anisotropy will work, and Nico Chandra has done that. So here then are just some pictures. So here are various single exponential approximations that depend on the orientation of the vector in the molecule, and I can't really tell the colors apart, but it works pretty well. And then, of course, we're usually interested in internal motions on top of the overall tumbling. And again, we're interested in the spherical harmonic in the laboratory frame. And just like Ann indicated, if we start in a principal axis frame, we can do a series of frame transformations to get from the principal axis frame, say the bond vector orientation in a molecular frame, to the molecular frame, to the lab frame. And it's exactly the same transformations as for solid state going from crystallite to molecular frame, or PAS frame to molecular frame to crystallite frame to rotor frame, except usually we don't have to do quite so many. And then we need the autocorrelation function, and we have to start making some approximations about what transformations are fixed angle and what transformations are time dependent. And again, things get very complicated quickly and require computer calculations, and certainly the future is more and more computer simulation and less analytical calculations. But a very common approximation is to say that overall tumbling is independent of internal motions. And that could be because they are independent. So the tail doesn't wag the dog, or because they're time scale separated. And independence is kind of a stronger statement than time scale separation. A lot of times you'll see in the literature, we mostly argue on the basis of time scale separation and get nervous if the time scales between overall tumbling and internal motion start to get close to each other. There are some papers about coupling between internal and overall motions. Michelle Gill, there's a very complete theory from Marius Clor's group that's extremely complicated. And there's a really elegant toy model from Dave Case that provides a lot of insight. In that toy model, the change in overall conformation was just going from a small sphere to a big sphere. And he was able to get compact analytical results. And then Michelle Gill in my lab took Raphael's isotropic approximation approach and applied it in Dave's small sphere, big sphere model. So what Michelle did reproduces quite well the full theory from Clor's lab, but much simpler mathematics. But even so, we don't yet really have strong experimental demonstrations and cases. That's still for the future. And then this partitioning goes completely out the window, of course, if you have IDPs or unfolded proteins. And there we still know relatively little about how we should quantitatively analyze the data rather than just looking for trends. But even if we make the assumption that overall and internal motions are independent, you still have this effect on orientation in the molecule. As I said, the CSA and the dipole tensor see different motions is because they're not collinear if the molecule isn't isotropic. So the simplest possible assumption is to say that the molecule is isotropic, and then the internal motions factor out completely from overall tumbling. So even independent internal motions have a dependence, are truly independent of overall tumbling in an anisotropic molecule. But that's something we mostly ignore as well when analyzing data. It's approximately true if the local motions are limited. So most of, motions are limited in a protein until they're not limited. And the not limited parts tend to be where you're most interested. So it's really still kind of the case that for a realistically anisotropic protein, that where you have, say, loops with extensive motions that you're interested in because of binding processes, etc., all of these approximations start to break down in ways that we don't really know without doing simulations. But if we assume internal motions are independent of overall motions are isotropic, then we end up with autocorrelation functions for the internal motions. And now we can say, what happens to this autocorrelation function if tau goes to 0? And then what's called the closure theorem shows that we sum to 1. And if tau goes into infinity, then we know that the autocorrelation function becomes the product of the averages. So here's the product of the averages. And that's called the order parameter, or the square of the order parameter. So the internal autocorrelation function is going to decay from 1 to a plateau called the order parameter, square of the order parameter. And the more restricted the internal motion is, the larger that will become. And if S squared became unity, then there's no internal motion. And if S squared became 0, that would suggest that the interaction could explore at least a hemisphere of orientations. So the order parameter becomes a measure of the amplitude of the sampled conformational space. And that's really nice. It doesn't depend on our model. It just depends on the property of autocorrelation functions. So in that sense, the order parameter is model independent. So then, of course, the autocorrelation function is going to decay somehow from an initial value of 1 to a final value of S squared. And that depends on the stochastic process for internal motion. Again, if fast bond vibrations go into the average of C's, then everything else is overdamped. And that means the autocorrelation function is going to be a sum of exponentials. And we can always define mean correlation time by taking the integral. The area under the autocorrelation function has units of time. And if I just do this integral, I see that over here, I have the weighted sum of all of the tau sub i's. And this led to what's called the Lipari-Szabo model-free formalism. And that says we can approximate the internal autocorrelation function, which is multi-exponential, by the limiting value, the plateau, S squared, and then an amplitude 1 minus S squared times an effective internal correlation time. And that internal correlation time is defined by this integral that I just showed. So it's the area, you match the area under the single exponential curve is matched to the area under the real autocorrelation function, which of course you don't know. People have strongly criticized this approach because Lipari and Szabo called it the model-free formalism. And they say it's not really model-free because you depend on the real internal autocorrelation function for determining tau sub b. I would say that's a little harsh because no matter what the real curve is, you can always calculate, it always has an area. So the mean of some quantity is about as model-free as you can ever get for that quantity. So whether you like the name model-free or not, this has turned out to be an extremely useful autocorrelation function. And as the autocorrelation function, it's used in fluorescence spectroscopy. As spectral density, it's used in NMR. At the same time, a very similar theory was developed by Halle and Venenstrom, which they called the two-step approach. And for historical reasons, this is the Lipari-Szabo treatment has been more adapted in practice, even though they're very similar in reality. And then if we Fourier transform, so there's the internal correlation function, we multiply it by the overall isotropic correlation function, Fourier transform, here's the spectral density function, we have the square of the order parameter, we have the overall tumbling time, and we have tau prime, which is the geometric mean of the overall tumbling and the effective internal correlation time. So it's a very simple 3-parameter model that turns out to be very useful for analyzing NMR relaxation data. And then here's the picture. We have overall tumbling of the molecule. We have some tensor principal axis, say the bond vector for N and H, and there's some wobbling of that vector, and then the order parameter becomes a measure of the amplitude of the conformational distribution, and tau sub b becomes a measure of the time scale for exploring that conformational space. And if you have some motional process, some stochastic process, and if you ask, what's the minimal information I might hope to find out, the amplitude of the fluctuations and the time scale of the fluctuations, are the two simplest bits of information. And this theory gives those to you. The amplitude of the motions is captured by the order parameter, and the time scale is captured by the effective correlation time. You may want to know lots of other things. You might like to know the mechanism of the motion. Is it a 2-site hop? Is it a 3-site rotation? Is it continuous diffusion on the surface of the cone? And the NMR relaxation data in solution is not going to give you much information about that. That was one of the great insights of the original Lipari and Szabo paper, was that many of these models gave equivalent order parameters and tau sub b's if you were fitting to data. The situation is becoming a little better now because we can collect data at so many magnetic fields that the information content becomes higher and higher. So one can apply more complicated models. That said, at high field, they certainly starting for NH at 500 by 500 megahertz, you're already in kind of a high field limit. We think, again, from work that Michelle Gill did when she was a postdoc, that agrees very well with similar work at the same time from Martin Blackledge and Fabian Farage, that the nitrogen 15 relaxation data contains about 5 bits of information. And that means you have information about an overall tumbling time, possibly 2 order parameters and 2 time scales for internal motion. And if you want more information, we have to explore different parts of the spectral density function, because even by 500 megahertz, we're already in the 1/omega squared decay part of these spectral density functions. So to get more information, we have to get to that point where they roll over. And that's proving very hard to do. The main approach is sample shuttling, moving the sample from high field to low field for the relaxation experiment and back again. And Fabienne Farage again in Paris has in doing the most along these lines. And we have a device downstairs here for doing it that we're also trying to make progress on. Well, it seems simple. The difficulty is while you're moving the sample and the magnetic field is changing, all of the relaxation rates are changing. You have to integrate the effect on the spin system while you move the sample. But to do that interaction, you have to know the dynamics of the molecule. But you're trying to learn the dynamics of the molecule by doing the experiment in the first place. So it's a very circular problem, but there's still work to do. Anyhow, here's an example. So I just made an autocorrelation function with 1, 2, 3, 4 exponentials, and then calculated the average decay from the Lipari-Szabo model, and black is the real 4 exponentials, and pink is the Lipari-Szabo approximation, and you can see it's a pretty good approximation. Here I changed the parameters, and now you can see it's not such a good approximation to the 4 exponential decay, but then we can extend this, as I already said, to 2 internal exponentials, and there's multiple ways of doing this, but basically we have a time constant and an order parameter for faster motions, and a time constant and order parameter for slower motions that we imagine are separated by like an order of magnitude. And then we can apply the same kind of approach as in the original model-free formalism to express the fast and slow timescales, the fast and slow order parameters. So here then is the result. Black was the 4 exponentials. Pink was the original 1 exponential approximation. And then blue is the 2 exponential approximation. And now you can see 2 exponentials are a quite good approximation to this 4 exponential autocorrelation function. And as I said, 2 order parameters, 2 timescales, and overall tumbling is about the best we can do with at least within 15 data at high field.
Now,
Yep.
one clarification. So here the correlation timescales for internal motion have to be much faster than tumbling, what we said.
So the Lipari-Szabo approach says the motion, internal motions and overall motions have to be independent of each other. Actually, the Hala and Venenstrom approach assume they were timescale separated from each other. In fact, most of the time, our tacit assumption is that they're timescale separated. And when we analyze in data, I'm not sure if I've shown you real data here, we tend to find in elements of secondary structure in a protein, most of the internal correlation times are around 50 picoseconds. And overall tumbling for ubiquitin is 4 nanoseconds. So there's pretty good timescale separation. In the loops or the termini, one will start to see timescales of a couple of nanoseconds. And there it starts to get a little bit unclear how much timescale separation there really is. You're pretty happy if you have timescale separation of an order of magnitude. But when it gets to be only 2, 3, or 4, a factor of 2, 3, or 4, just to be a little nervous as to how well that separation is.
But I guess my question is, if I were to measure R1 or R2, what time scale window for internal motion cell I directly sampling? Is it all motion cell or faster over tumbling?
So if we come back here to this expression, right? Suppose there are motions, the tau sub b is much slower than overall tumbling. Then this won't have decayed. And the whole autocorrelation function will have decayed from overall tumbling. So internal motions that are much slower than overall tumbling become invisible to this experiment. Because once you've randomized all orientations by overall tumbling, there's nothing left to be randomized by the internal motions. And you see this if you compare, for example, you can estimate order parameters from residual dipole couplings. And in the cases where this has been carefully done, for example, in ubiquitin by Christian Griesinger, Raphael Bruchweiler, Martin Blackledge, the order parameters from RDCs tend to be somewhat lower than the order parameters that come from relaxation measurements. And that's because the relaxation measurements are sensitive to motions on the time scale or faster than tau c. And the RDC measurements are sensitive to motions out to a time scale roughly the reciprocal of the residual dipole coupling constant. So that's out to milliseconds. So you pick up motions that you don't see in relaxation. And if you run a 2 millisecond MD simulation and calculate the order parameters over the 2 millisecond or 2 microsecond MD simulation, you tend to find order parameters that are lower than the NMR measurements, because even in 2 microseconds, you start sampling motions that are slower than tumbling and don't contribute to the NMR result. And of course, if motions get slow enough, then we start to pick them up in relaxation dispersion experiments, but there's a missing window, and you know, year by year, people try to narrow that window.
That window be close to correlation time, but not much slower than the tumbling time.
Right, so slower than the tumbling time, but faster than say 10 microseconds,
Right.
which is where kind of solution relaxation dispersion experiments, let's say 1 microsecond to be optimistic, start to get really difficult. So you have a factor of say 100 missing. So the order parameters are always an equilibrium property of the system. They just depend on the distribution of angles. They don't depend on the times. And that means that we can always calculate them if we have a probability distribution or orientations in the bond vector of the bond vectors. And we might have that from a simple model, or we might have it from an MD simulation, but it's essentially an integral. So here's probably the most common model. The bond vector can move freely within a cone. The walls of the cone are rigid and reflecting. So the bond vector hits the wall, it just bounces off. So in that case, the integral, or the probability distribution is just 1 over the volume contained inside the cone. And then if we do the integral, we end up with a simple result for the average of the spherical harmonic, and then that turns into a simple result for the order parameter that just depends on the cone semi-angle. So if you look back in the literature, you know, it's quite common for people who measure the order parameters to convert them into the effective cone semi-angle to get an idea of roughly how large of fluctuations are we talking about, say for the bond orientation in secondary structure. And depending how you do the calculation, it turns out to be just a few degrees, which would make you happy. When if you have an alpha helix with the NH hydrogen bond, it's hard to imagine how that deviates by more than a few angles without having to break the hydrogen bond. Well, one can play this game, since many integrals can be done. Another model is diffusion on the surface of the cone. So this is like a rotamer, right? We have a fixed angle, and the dihedral angle is just varying in time. And if you're just stuck in the bottom of the well, not making jumps, then you just have libration in the bottom of the well. So here's a potential probability distribution. It's called the von Mises distribution in the literature, and we can integrate it. These functions I are Bessel functions. And here's just some pictures. So blue is diffusion in a cone, and pink is diffusion on the surface of a cone. And obviously there's diffusion on the surface of a cone. There's some limiting value of the order parameter, because all you can ever do is go all the way around the cone. You can't explore all space. So there's just two examples. The correlation times are much trickier to calculate. You have to solve some kind of equation of motion, and there are fewer expressions in the literature for correlation times than order parameters. For the diffusion in a cone, here's an expression for the effective time constant in terms of a diffusion constant for moving in the cone. And it's complicated. We can test this if we want. I just ran a little computer simulation for diffusion in a cone. So I have a bunch of dots starting at the North Pole, and they can spread out, but they can't leave the cone. So you can see they just explore the cap on the surface of the Earth rather than going all around the Earth. And then here are the fluctuations in the polar angle. And then I think black is the correlation function calculated using the equation for the time constant, and pink is the simulation. And they agree pretty well. So again, the future is more simulation, I think, and less analytical calculation, because obviously I can make the potential in the computer as complicated as I can think up, and then just run simulations until I get bored with simulations. The other model beyond diffusion, just to finish quickly, would be jump models. So now if you think about, again, rotamer, if you ignore the librations in the bottom of the well, then you have jumps over the barrier between gauche plus, gauche minus, and trans, for example. So jump models also have a formal way of calculating the autocorrelation function or the order parameters. And again, the simplest is to calculate the order parameters, given that we know the populations of the three rotamers, say for a 3-site jump. We know the populations, and it's straightforward to calculate the order parameters. I think I went through the math here for actually calculating the autocorrelation function, and it's not so interesting. So I'll leave it for you. If you like matrix math, you end up with, for a 2-site jump, something that we can cast as the Lipari-Szabo-like model. We have an order parameter, and then we have something that depends on the populations and the forward and reverse jump rates. But that's mostly there if you like doing matrix math. Again, if you wanted to do a calculation in practice, you would fire up spinach, and spinach would do all this for you without you having to know anything about the matrix math. I think we can stop there, and that kind of completes VWR theory. We have expression for the rate constants, and now we know something about the spectral density functions. So our other issue is what happens when we're not in the red field limit. And that leads to relaxation dispersion, Bloch-McConnell equations, stochastic Liouville equations. So that has to come up in the future. That may be after the ENC, because I'll be at the ENC. Next week is spring break at Columbia. And then the week after, I'm at the ENC. So it may be that, and we'll talk about solid state pulse sequences, and then we'll come back to out of the red field and relaxation. But I'll have Whitney send out a modified syllabus once we finalize what's happening the week of the ENC. Any questions online?
And then the synapse is there will be measurements and over function configuration.
And when did you say you went to ENC?
The ENC, oh no. Next week is spring break. Oh, I'm not at the week after ENC, I'm teaching at Ohio State. So next week is spring break.
Oh, I see.
Then I'm teaching at Ohio State for a week. So that'll be when Ann talks, I think, about pulse sequences. And then the ENC problem is still in the future.
Yeah.
Okay, everyone enjoy spring break, even if you're at a school where next week isn't your spring break.
So,
Do you have any scheduling conflicts in May?
No, May, I'm actually around. Pretty much all of May by some miracle.
Oh, perfect.